Hello everyone, my name is from University of Wisconsin-Madison. Today I'm going to present our paper, Enabling High Precision Visible Light Localization in today's buildings. So indoor localization has a broad range of applications, such as user navigation in a large building, the consumer footprint analysis, the entertainment such as VR and AR, and also the targeted advertisement in a retail store, and drone tracking. But most of these use cases are still under conceptual development and have not been widely deployed yet. It is mainly because of the challenges in satisfying all these four practical requirements. First, to keep the cost low, we have to reuse existing infrastructures and commodity devices. Such system has to be robust and accurate to overcome the environmental and user behavior changes. This system must be power efficient to support continuous real-time localization on mobile devices. There are quite a few existing solutions trying to tackle this problem. The radio-based localization has low cost, however it suffers from multi-pass effect and environment dynamics. Same uses a stereo camera with complex image processing. So the power consumption and cost are big issues. The existing visible light localization uses beacon-based smart LEDs to act as light infrastructure. Although it is both robust and accurate, it requires specialized LEDs to replace all the existing light fixtures, which requires very high cost. So here we propose a new paradigm for indoor visible light localization that can overcome all these limitations. Our system is called İLAMP. And like other visible light localization-based approaches, the most important step of İLAMP is to distinguish different marks, so they can be used as location landmarks. But instead of using the spectralized LEDs, we use existing LEDs and fluorescent lights, which are already available in today's buildings. But the lights inside one building, they usually share a very similar look. So the question is, how do we distinguish them? The famous Japanese Leibniz once said, no two leaves are ever exactly alike. And the İLAMP's key observation is that no two lights are ever exactly alike. More specifically, the lights inside the building contains the hidden optical and visual features that can be captured by the camera and image processing on the smartphone. By combining with other sensors on the smartphone, we can not only ensure the uniqueness of the features, but also provide the relative position between the smartphone and the light landmark. Let's first look at the framework. To set up such system, we first capture light features and their physical locations and store them into a central server database. We run in the İLAMP, a smartphone captures an image of the nearest light and send this process the image data to the server, and server will tell you the physical location of this light. We further design a sensor-assisted photogrammetry method to calculate the relative position between the smartphone and the light landmark. To take the power consumption, we design a camera scheduler, which can adaptively turn on the camera. Finally, in the blind area where no lights are visible, we use alternative motion tracking method to complement İLAMP. So the first thing is, let's look at how İLAMP identifies the light. İLAMP uses three features to characterize each light. One main feature and two assistant features. The main feature is called spatial radiance pattern, or SRP. The SRP reflects the radiance distribution across the light's body. The SRP differs among lights mainly because of the manufacturing variations, such as the density and distribution of the phosphor layer inside the light. And this graph shows the SRP of 4 fluorescent lights and 4 LEDs from the same model, and they are quite different. To identify a light, we first capture the SRP of a light and match it with the Y in the database. But the smartphone's pose may have some distortion, because some distortions on the SRP feature. So we use the method called dynamic time warping as a light matching algorithm, which is well known to overcome such distortions. To further make the light more unique, we combine our main feature with two assistant features. The first one is called infrared visible light intensity ratio. The ambient sensor on the smartphone has two photodiodes. The first one only measures the infrared light, and the second one measures the visible light as well. So the ratio between these two intensities can help us to distinguish the light. Also, we found that color temperatures are slightly different across different lights, mainly because of the imperfect manufacturing process. And this color temperature can be directly extracted from the light's image and can be served as an assistant feature as well. So the next question is, how do we combine these three features together? Here we use a hierarchical way. First, we use assistant features to filter the light candidates inside the database and narrow down the search space. We then use the main feature to make a final decision and return the physical location of the best match light to the user's device. The SRP and color features are extracted from the light image. However, the camera's hardware has artifacts which will affect the feature extraction. Actually, the camera's image sensor contains three colors, which will create noise on the SRP pattern. So we remove this artifact by normalizing the intensity of each color. Second, the lens center part is brighter than the edge part, which we call the magnetic effect. So we compensate this magnetic effect by using a feeding curve. The light identification can tell us the physical location of each light, which always translates to meter level accuracy. So in ILAMP, we further increase the location precision by designing a sensor-assisted photogrammetry. The idea is simple. The physical location of the light changes with different points of view, which infers the relative position between the smartphone and the light landmark. We use the gravity sensor because it can provide the information about the phone's pose. And actually, camera captures the projection of the light on the image sensor instead of the light itself. So we designed a geometric model that can translate this projection result into smartphone 3D locations. Camera is a power-hungry component on the smartphone. So we designed a camera scheduler that can adaptively turn on the camera only if the light is visible to the camera. But the question is, how does the smartphone know whether the light is visible or not when the camera is turned off? So here we use the ambient light sensor. We found the fraction of the light body inside the image captured by the camera has a strong correlation with the light sensor's readings. So this strong correlation can be leveraged to duty cycle the camera. And the parameters that characterize this relation can be trained offline. This figure shows a power snapshot monitored on the smartphone when user is moving, is holding the smartphone and running ILAMP and moving across the hallway of the building. You can clearly see that this camera scheduler can adaptively turns on the camera corresponding to the locations where lights are visible. So we have implemented ILAMP and verified its performance through comprehensive experiments. We tested ILAMP across these 4 buildings with hundreds of lights each. Our experiments are conducted based on current prototype with the central server database and Android application, which is for a year. So our experiments confirm that ILAMP can identify a light with around 90% accuracy under a single light, even with our main feature. And by combining these 3 features together, we can achieve around 98% accuracy. We further tested the location granularity of our sensor-assisted photogrammetry. And this figure shows the CDF of location area across randomly selected capacity locations. Here we can clearly see the 3 centimeter precision average can be achieved under a single light. And the static percentile is 3.2 centimeters. Also, we found if multiple lights are in the camera's field of view, we can even improve the location granularity. Many multiple factors in the practical scenario will disturb the robustness of the system. So, we found İLAMP can handle such practical uncertainties very well. First, İLAMP can still maintain high accuracy even if the setting is very high and the camera has a moderate resolution. Second, according to our test, our 3 features are stable across months. Third, even if, although the smartphone's host may distort the image, İLAMP can still maintain high accuracy under such distortion. Finally, even if the camera is shaking when the user is walking, we can still maintain high accuracy. So we conducted 2 field tests here. The first one is in our research lab, where lights are densely deployed, and we can always maintain centimeter level accuracy here. And the second one is done in our research building, along the corridor of the research building, where the lights are sparsely deployed along the working direction. So recall we use that reckoning when our camera is turned off by our scheduler. The reckoning has a cumulative drift problem, but İLAMP can correct the drift, but not is visible. And we also found İLAMP is suitable for real-time localization. With 500 lights, the latency can be under 1 second, and it can be further reduced by software implementation optimization. As for the power consumption, our current camera scheduler can save more than 50% power in our current building capacity, and it can save more if the lights are more sparsely deployed. So to conclude, this work shows that the indoor localization can be done in existing buildings and current buildings with existing light infrastructure and commodity device. Our key observation is that the existing light infrastructures already have enough rich optical and visual features, so the lights can be regarded as good location landmarks. Finally, by using the geometrical analysis and sensor fusion algorithms, we can not only improve the location precision, but also maintain the reliability of our system and ensure the power consumption is low enough to support continuous real-time localization. That's all from my today's presentation. Thank you.